So in today's lecture, we are going to talk about optimization problems in deep learning. So here is our agenda for today's lecture. Optimization problems in deep learning. And in particular, we are going to focus on the role of over-parameterization. In deep learning optimization problems. And as you'll see in this lecture, next lecture, and also in a couple of lectures that we are going to spend on the generalization, over-parameterization is in fact very important aspect of many deep learning problems that we'll look into. So last time we started with an ERM problem. So we are getting a training set and we are minimizing our weights W based on the average loss of our model over training samples. So I have 1 to n loss of fw of xi, yi. Again, just to recall the notations that we used, x is there in d dimension. Let's say we are looking at the classification problem with C labels, so while y will be in a finite field with C elements. And the question is how to solve this optimization problem. Because in general, we will have a non-convex optimization problem, because for neural networks, f of w is a nonlinear function and the whole objective will be a non-convex problem. And we saw some pictures. If we had a convex loss, if my loss was like this, I was very happy because I can use gradient descent or stochastic gradient descent, follow the negative direction of my gradient, and eventually converge to W star. And this was good, we were happy. But in the non-convex case, we argued that the loss can be very complicated. So we may have some bad locals. So this is my W star. But here I have a poor or bad local. Or we can even have like some saddle points. These are the points that the Hessian they have, it has both positive and negative eigenvalues. So you may have like some, saddle point problem as well. Right, but interestingly, in practice, when we run gradient descent or a stochastic gradient descent, they work pretty well to optimize deep learning optimization problem. They work pretty well. Not always, but in many cases, they converge to pretty good solutions. So the question is why? So we know we are in a non-convex setting, and we know in the non-convex setting, we have a lot of issues. We have poor locals, we can have saddle points, but surprisingly and somehow magically, a stochastic gradient descent or gradient descent, they converge to pretty good solutions. And this was a topic of a lot of interesting research in the last couple of years in foundations of deep learning. All right, so today I'm going to mainly talk about the recent work by Liu, Zhu, and Belkin. It's a very recent work. I think the draft was on arXiv in February 2020. So we posted the paper on course webpage. I'll follow some part of the paper during this lecture. So let's start with some intuition. So one key practical observation is that in most successful deep learning implementations, the training error, this is the error that I compute over samples in my training set. It can be very small, almost zero. So remember, in our training, our goal is to find a function fw mapping x to y's, right? And if my function is able to basically approximate well each y in my training sample, I'll have a very small training error. So in terms of generalization, we'll talk about it in the next lectures, but just focusing on the training error, so we can almost get a zero training error in general. And why is that the case? Because usually the models that we use, the deep models that we use, they have a lot of parameters. And so the models, they have a lot of flexibility in terms of interpolating my XY relationships in my training set. Right? So that is basically the main reason. So in general, interpolation, so when we have a zero training error, this is basically interpolation, because I'm interpolating XY relationships almost precisely using a neural network that I'm using as my model. So in general, interpolation is possible, especially when the number of parameters in my model is larger than the number of my training samples. Right? So if you have, let's say, 10 samples, you have 10 x's that we want to map those x's to y's, and then you have, let's say, you're using a model with 100 parameters. So you have 100 degrees of freedom, roughly speaking, and you have 10 equations that you want to map x's to y's. So you'll be able to achieve almost zero error in such cases. So we'll basically call the number of parameters m for our model. And the number of samples, I'm going to refer it with a small n. Remember, the capital N is the number of training samples we have. But for each sample, my label can have C classes, right? So in order to achieve like the exact interpolation, I want to make sure that I'm predicting each of the components of my labels correctly for each sample. So in other words, I have n data points that I want to interpolate. And we say we are in an over-parameterized regime when my number of parameters m is larger than my number of samples. So this is called over-parameterization or over-parameterized regime. Okay, so I see there are some questions. Let me pause. Right, so there's a question. It says, when the number of parameters is larger than the number of samples, when we are in an over-parameterized regime, isn't bias overfitting huge? This is an excellent, excellent question. And in fact, our intuition from classical results of bias variance trade-offs may indicate that, okay, so you have now a lot of parameters and you have few training samples. Then even though your training loss is small, then your test loss or your validation loss is going to be huge, and you are going to suffer from overfitting. Does this happen, in fact, in deep learning and neural networks? So for that, you should wait for the generalization lectures. And in fact, that is not happening in general. So we'll cover some of the recent results explaining that very, very interesting phenomena as well. All right, so there's another question. Isn't interpolation also a function of, loosely speaking, how difficult the data distribution is? Yes, so if you have a simple relationship between your x's and y's, let's say x and y's, they have a linear relationship, then you don't need a lot of parameters, right? So you can use even fewer number of parameters than the number of training samples, and then you will be good to go. However, in many real data sets, like say images and in mapping images to the labels, then you will have a very complex relationship between inputs and outputs. And the power of neural networks is that you can over parameterize them in order to, even in those complicated situations, to precisely interpolate input-output relationships. So there's another question about C. C is the number of labels we have. So here the setup is my Y here is basically we have a classification problem with C labels. So that's why in my interpolation, I need basically to interpolate N, which is the number of samples I have, times C, which is the number of labels for each sample. And I want to be able to interpolate all of the basically assigned probabilities or all of the assigned labels for each sample precisely. So that's why we have capital N times C as our little, as our small. All right, so for growing the number of parameters, can we talk about horizontal vertical growth of the network? Yes, I'll talk about that later on. In case of over-parameterization of linear system, won't the system be having many solutions? Yes, we'll see some examples of that. Okay, so I'll basically continue and take more questions later on. Okay, so let's look at some examples. Hopefully it will answer some of the questions that you have already asked. Let's look at the exact interpolation regime. So what do I mean by exact interpolation regime? Let's say I want to interpolate x1 to y1. Let's say y1 is class 1, but remember I have C classes, right? So this vector of y is in RC. And I have fw of xn, this is my last training sample, is equal to yn. Again, let's say, suppose the label is the last label for this. So I'm going to summarize these equations. So each sample, each training sample, basically adds C constraints to my system. Suppose C is 1, basically it adds 1 constraint for each training samples. So I'm going to summarize all of these constraints or all of these equations that I want to satisfy for my interpolation using this big function f. So I'm going to say my system of equation is f of w and x to be equal to y. And I know x, what is x? X is a big matrix of my training data. Say x is a matrix, d n by d. So this is my training samples and why they're my labels. All right, so we are going to abuse a little bit of notation here. I'm not a big fan of it, but this is how it is done in the paper. But I can see the rationale behind it. So we are going to make X implicit in our equations. So I'm gonna instead write if W is equal to Y, because X here is a constant, so it doesn't depend on the model parameters. When I write if W is equal to Y, here basically X, we should keep in mind X is implicit. So we do have X, but it is implicit in this equation. So if W is equal to Y basically represents all of the interpolation equations that I want to satisfy. So what is the dimensionality of W? So I have M parameters. What is the dimensionality of Y? I have N equations that I want to satisfy. And F is a function from Rm to Rn. Okay. So let's look at some examples just to get a feeling about it. It's a little bit abstract at this point, but it is actually really, really simple. It is even like a very, very basic just reformulation of the problem. Let's do some warm up. Let's say my number of samples is 1, n is 1, this simplest case. Let's say I have 2 parameters for my model, and let's say the dimension of my input is 1. So I'm gonna bring back X here because, it will, makes more sense to write it in this form. But we know X, even if I don't write it, X is implicit in my equations. So if W in this case is W0 plus W1 times X, it is a linear system. And I want this to be equal to my label. So I have one X and one Y. I have one training sample, and I'm fitting a model with 2 parameters, W0 and W1, to this sample. So how many solutions I can have? I can have a lot of solutions. So if I look at this line, so here, this is X over W, Y1, Y over X, and this is Y. So this is the line of all of my solutions to solve this system of equations. Basically, this is the manifold of all of my W stars. It's not unique because I have more parameters than number of samples or the number of equations I have. So I'll have infinite number of optimal W stars. And in fact, you see they are not isolated. So they form a manifold in this example. So you can, just to get a little bit of a better feeling, let's say now I have 2 samples. And let's say I'm using a model with 3 parameters. Again, I'm using a linear model. And let's say my samples are in 2 dimensions. So in this case, what's going to happen? So I have 3 parameters. Let's say W0, W1, W2. So I have 2 samples. So basically I have 2 equations. Each of them is going to give me a plane, right? So let's say I do have one plane. So these are the solutions that satisfy my first equation. And let's say I have this plane for my second equation. So I'm going to look at the intersection of the 2. So this intersection is the manifold of my W stars. Okay, so these 2 examples, just to warm up, they were like linear. What about nonlinear case? It is basically the same. So in the nonlinear case, so what I'm going to have nonlinear manifold satisfying each of my equations. So let's say I have this manifold satisfying if W of x1 to be equal to y1. This is my first equation for my first training sample. And let's say I have another manifold satisfying my second equation. It's fw of x2 is equal to y2, right? So this is interpolating my second training sample. And if I look at the intersection of the two, then this is again going to be my w stars. I just want to have this feeling about the set of equations that we have here, which is basically fw is equal to y. And we want to satisfy these set of nonlinear equations that we have here. All right, so one question is how I can solve these sets of nonlinear equations potentially, because in the linear case it is easy, I can solve it, but in the nonlinear case I want to find a solution in the intersection of all of these nonlinear manifolds. In order to do that, we can just define a loss function and optimize that loss function. So we have, let's say, a quadratic loss. I look at the difference between fw, so this is the numbers I'm predicting for my interpolations, and I want those numbers to be equal to y, so I'm going to use a quadratic loss. And the idea is just to formulate this optimization problem over w. And obviously, again, this is basically a non-convex optimization problem, right? So if my f is non-linear, this will in general be a non-convex optimization problem. It is more general than just neural networks, so you can think about other nonlinear functions to be used for your mapping. So this is a pretty general framework. So how I'm going to solve this? I'm going to use gradient descent to solve this. So what is the gradient descent update? So I'm gonna start with some random initialization, and I'm gonna say my weights in t+1 iteration is equal to my weights at t iteration minus eta, which is my learning rate, times the gradient at wt, gradient of my loss at wt. Right. So the whole today's lecture is about understanding whether or not gradient descent would converge would converge to what? Would converge to W star, right? Because we want to find a solution that results in zero training error. So that's basically the question that we'll try to answer in today's lecture. Okay, so let me pause and look at some of your questions. All right. I apologize if I'm missing some of the questions. I'm trying to follow all of them, but there's a chance that I'll be missing some of the questions. Is the phenomena you mentioned the double descent phenomena? Yes, so we'll talk about that later on. What if it is a regression problem and we don't have labels in definition of C? That's completely fine. So in the regression problem, if you're predicting just one variable y, then your C is equal to 1. If you're predicting C variables, then you'll have a larger than 1 C. So C not only is the number of labels, it's basically the outputs, the number of outputs of your network. It's a multi-class problem, yes. There's a question, usually more number of samples is desired for better generalization in deep learning, given the equation m greater than n for interpolation. Would that be a negative effect for achieving zero training loss if the number of parameters is fixed? Yeah, that's in fact, the subject of the generalization, right? So, let's not worry about generalization at this point, right? So in today's lecture, let's just focus on the training optimization. So we'll see some very interesting results about the generalization later on. Should it be W1 on one axis and W0 on other axis? Yes. Oh, perfect. You guys are awake. That's a good sign. Okay, so let's move on. All right, so this is the optimization problem that we have. Okay, so if we were in an under-parameterized regime, right? So let me actually go to our next page. If we were in an under-parameterized regime, this is the case when we have fewer samples, fewer model parameters than samples. Right, so we have a lot of samples, few model parameters. In fact, the picture I draw can happen. Like we can have all of these issues. We may have poor local here. We can have saddle points. This is my poor local. So if I start from somewhere here, so I'm going to converge to this point while my W star is here. But interestingly, in an over-parameterized regime, we should have a different picture in mind. And that's one of the messages of this work. So here we have manifolds of solutions, right? So our solutions are not isolated from each other, as you saw in the previous examples. You see, like we don't have just a unique solution in one point, and then nothing else is happening there. So the solutions are somehow coming in a manifold form, and they are not isolated. So what happens? We get some lost landscapes like this. So I'm gonna draw a picture. Hopefully it will be clear, but you can look at the paper for a better visualization. Right, so let's say the blue is my loss function and red is the manifold of W star. So again, these are not isolated, right? They, like similar to the previous case, in general, we'll have a figure like this for our loss function when we have over parameterization. Right, so that's basically the key difference between under parameterization and over parameterization. So there's a question by isolation. I mean, these solutions are somehow connected to each other. Right? So it will be clear in a minute what I mean by that. All right, so now we have this difference between the landscapes of our loss functions. There is another fundamental difference between the two. Okay, even though we have here poor local, let's look at the neighborhood around this point. Right, so if I look at a small neighborhood around my critical points, let's say this is my poor local, this is locally convex. So that's good because maybe in a small neighborhood I can use the convex analysis in order to say, okay, now my gradient descent is going to converge to a solution because it is locally convex, but that critical point may not be a good solution. But what about this picture? So if I pick a particular W star here, let's say I pick this one, and then if I look at the local neighborhood around this. So one interesting observation is that we don't have local convexity in these neighborhoods. Here we have not, they are not even locally convex. So this is what we call essential non-convexity. The fundamental difference between under-parameterized and over-parameterized regimes. In under-parameterized regimes, you converge to a bad local, you look at your neighborhood, you are still locally convex, globally you are non-convex. But here in over-parameterized regime, if you look at a neighborhood around your W star, then essentially you will be non-convex, meaning that you are not even locally convex. So why is this the case? Let me explain this in a high level. So first of all, we know minimizers of convex functions, they form convex sets. Minimizers of convex functions form convex sets. Now let's look at basically a manifold of W star with curvature. Let's say, you know, I have curvature. It is not just an affine manifold, because if you have nonlinear equations, what are the odds that you'll get an exactly affine, you know, manifold for W star? So it is very unlikely. Let's say my manifold of W star has some curvatures. So I'll basically get a shape like this. Right? So let's say all of the solutions over this manifold, they are my W stars, including, let's say, W0 and W1. And I know the solutions for convex minimizers of convex functions, they should form a convex set. So in other words, if I connect these two, this line should be in my my set of solutions. But I know, let's say for instance we have W prime here. But I know this W prime, the loss value cannot go below the loss value at W0 and W1, right? Because these are the minimizers for my loss. So here, because W prime is on the line between W0 and W1, so it should be, the loss should be lower than W0 or W1, but we know these are the minimizers, so these are my minima. Then we conclude that W prime should also be in my set of solutions for my W star. So with that, you can argue. So I'm not, you know, going into the details because, you know, I want to spend a little bit of time on some other more important proofs. The manifold of W star should be affine, should be an affine subspace. So it cannot have curvatures. Right, so now you can argue maybe we can have nonlinear systems of equations, but magically they provide like an affine subspace. There are some arguments in the paper about that, but in general, it is very unlikely that if you have nonlinear sets of equations and the manifold of W stars, they happen to be affine subspaces. So because of that, we will not be even locally convex around any of these points. In other words, if I look at the Hessian values, in some of the elements will have, you know, positive eigenvalues, and some of the directions will have negative eigenvalues. So we cannot use convexity, local convexity, in our analysis. So the takeaway message here is we cannot rely on convex analysis to understand the theory of optimization in the over-parameterized system. So theory of optimization for over-parameterized systems cannot, or perhaps should not, be based on convexity, right? Because we are even non-convex locally, so we cannot use convex analysis to tackle with this problem. Okay, so let me pause and take some questions. So there is a question why loss at W prime is less than loss at W0. So this is a convex function, right? So you have 2 points, W0 and W1. So your function to be able to be convex, it should go below that. But we know W0 and W1, they are minimizers. So because of that, it should remain affine. Right, so I repeated the argument. Yeah, the question is it provable that the neighborhood is not locally convex? Yes, I gave hand wavy proof here, but take a look at the paper for a little bit more concrete arguments. But eventually, so what it says is that we cannot have curvatures, right? So if you have curvatures, you cannot be locally convex, and you can argue that when you have large nonlinear systems, you won't get, and you'll always get some curvatures in the manifolds of your solutions. Okay, so let me move on. All right, now we cannot use convexity. Then what can I use? So let me also look at the time. Okay. So instead of convexity, we are going to use some results called PL conditions. Polyak, I'm not gonna dare to pronounce the second name. So I'm gonna refer the whole thing as PL conditions. It is a result from 1963. So it has a very simple form. It basically says, okay, look at like some neighborhoods. Let's say my neighborhood is B. Even in this neighborhood, if I could show the magnitude of my gradient, magnitude squared of my gradient is larger than, let's say, a constant number, mu, times the loss function. So you compute the magnitude of your gradient squared. If it is greater than mu times the value of the loss function, then you have exponential convergence of gradient descent in that region. Really, really elegant and simple condition. This is the PL condition. And we'll see a variation, a proof of this, hopefully in today's lecture. But you can see, it doesn't assume anything about convexity of the loss function here. So the only condition that we want here is basically this PL condition or mu PL condition when the gradient square of the magnitude square of the gradient is greater or equal mu times the loss in all points in that region that we are considering. Okay, there's the actual PL condition is in fact a little bit different. So I will add a note here. The actual PL condition says the gradient square should be greater or equal to mu times loss at W minus loss at W star. But we don't know W star, so it is harder to show if my function satisfies this definition of the PL condition. But if I could satisfy this PL star condition, it's a small variation of the PL condition, you can immediately see that will satisfy the actual PL condition as well, and will be able to prove the convergence. So therefore, we are going to only focus on this condition that we have here. So the question is, now if you give me a neural network, right? Let's say I have a deep learning based model. Do we have, let's say, PL with some constant mu in a region, right? So I know it is not convex, but can I say something about the PL condition? And if I could say something like that, then, can I use these results in order to argue the convergence of the gradient descent? Okay, so let me take some questions. Geometric interpretation of PL condition, we'll see that. Hold on a second. Okay, yeah, exponential convergence, yes, means linear. So there are different terminologies in the literature. So we'll show the precise evolution of the loss function. So that will be clear. So there is a question of what is mu. Mu is a constant, right? So we want this mu to be as large as possible, ideally. Okay, so let me move on. So in order to have a little bit of a geometric interpretation of the PL condition, so I need to define tangent kernel. And in fact, in one of the lectures, we are going to dig deeper into neural tangent kernels. But tangent kernel is a general concept for nonlinear or even linear systems of equations. So tangent kernel for a system of equation, f of w is equal to y. Again, my w is in m dimension. These are number of parameters. Y is in n dimension. My tangent kernel, k of w, is a matrix of size n by n, based on the number of equations that I have or the number of samples that I have. It is the gradient of my function f at w times its transpose. Nothing complicated. So this gradient is a matrix of size n by m, and the transpose is a matrix of size m by n. So altogether, you'll get a matrix of size n by n. So you give me a set of equations, so I can just compute the gradient of f and multiply with its transpose, then I'll get basically my tangent kernel. All right, so why this tangent kernel is important? Because of the following lemma. Right, so so this tangent kernel is a positive semi-definite matrix, right? Because it is in the form of like a matrix times its transpose. So in other words, all of its eigenvalues are non-negative. But if I look at the minimum eigenvalue of this guy, kw, my tangent kernel, over the region that I have, if the minimum eigenvalue is bounded away from 0 by a constant mu, then I have PL condition with a constant mu on that ball, that I have for my parameter space. Right. So basically, in order to show a system of nonlinear equations, they satisfy the PL condition. Therefore, if I minimize the loss function with gradient descent, I'll have a convergence to my W star. One way to do that is to form a tangent kernel for that neural network, and then show that the minimum eigenvalue of that is greater than mu, is greater than a particular constant over a region of parameters that we are considering, and that's it. And then I can show we satisfy the PL condition, and then using some results, classical results, we can show the convergence of gradient descent or stochastic gradient descent. All right, so let me pause and take some questions. Yes, B is the neighborhood. Let's say you start with some initial point, W0. Right, so in general, we are going to do this practice. Let's say you start from W0, you run your gradient descent, you go to W1, you go to W2, then you go to WT. And we want to look at the region around our input, let's say B, that includes all of these possible W's that we could visit using gradient descent or stochastic gradient descent. So are we assuming LW star is 0 so that PL star condition implies PL condition? No, not necessarily. So because loss is non-negative, then PL star condition will always imply PL condition. But even if you need to assume LW star is 0, the loss at W star is 0, that's fair. So it's not a big deal. Okay, so why do we have to find the minimum eigenvalue of the tangent kernel and compare it with the W star? So yes, I'm going to basically show why this is the case, right? So the question is why the minimum eigenvalue of the tangent kernel implies the mu PL condition. Okay, so let me move on to the proof. The proof is in fact quite simple. Right, so let's start with the definition of the PL. Right, so in the definition of the PL, actually, there's a half here. In the definition of the PL, I want to have a lower bound on the magnitude of my gradient. So let's start with that. So I want to bound the magnitude of my gradient. And this result is in fact true for the quadratic loss function. So my loss function here is in the form of fw minus y squared. All right, so what is the gradient of this guy? So it's a quadratic, 2 and 1 over half will cancel out. We'll get fw minus y times the gradient of f with respect to w. Right? So we'll basically have fw minus y, there's a transpose here, times the gradient. All right, just to check the dimensions, always good to check the dimensions. So this gradient is a matrix of size n by m. So this fw minus y is a vector, a row vector, size 1 by n. So this whole thing is going to be a vector, a row vector of size 1 by n. And that's basically what we have here. So if you want to do a column vector, it doesn't matter. You just add a transpose. Okay, so we have a vector. I'm looking at the norm squared of a vector. So that's equal to VV transpose. Therefore, I can just write this as this vector, the row vector, times its transpose. Fw minus y times the gradient. So this is the vector that I have. There's a row vector. I'm going to multiply with this transpose, which will be gradient transpose times Fw minus y. Okay, so now you can see where this tangent kernel is coming into the picture. So this guy, the gradient times gradient transpose, is nothing but my tangent kernel here. And I know my tangent kernel from the lemma, it is minimum eigenvalue is bounded away from 0 by mu. So this whole thing, therefore, is going to be greater or equal to 1 over half lambda mu of this tangent, lambda min of this tangent kernel, times what? Times this guy, Fw minus y transpose, times Fw minus y, which is the norm of Fw minus y. And that's it. Because if you look at this half and then you look at the norm of FW minus y squared. So what is it? It is just my loss function. Yes, very good. So this will be equal to lambda min of kw times my loss function. So basically, I showed my magnitude of the gradient is larger than lambda min of my tangent kernel times the loss function. So if this lambda min is bounded away from 0 by mu, then I have the PL condition. Really, really simple, basic stuff. So therefore, all I need to show for the convergence is to show that this guy is the lambda min of my tangent kernel in this ball that contains the W's that I'm visiting using gradient descent or stochastic gradient descent is above a certain number, is above a certain mu. Right, so let me pause and take questions. Yes, so there's a question about the computability. Yes, we can compute tangent kernel. So for neural networks, in fact, I'll spend one lecture just to show even some closed form solutions for tangent kernels. SGD converges to the global. If I have a mu PL condition, it will converge to the global solution within the ball that I'm considering my mu PL. So that's the very powerful consequence of the PL condition. Should be greater or equal to. This lemma is only true for the quadratic loss, but I can imagine that you can, argue similar results for other loss functions. Why is it called tangent kernel? Because you're looking at the gradient, right? So gradient is a tangent, plane to your, loss function. So that's why it is called tangent kernel. Okay, good. So I'm probabilistically sampling your questions. Hopefully we will address, enough of them that will cover, most of the questions. So let me move on. So first I'm gonna show the informal result of the convergence, and then I'm going to dig a little bit deeper into the results. Informal convergence result. And baby. Right, so basically the result says gradient descent converges exponentially fast to a solution, to a global solution with the rate. What is the rate of the convergence? With the rate controlled by this quantity. So we define a condition number for set of nonlinear equations that we have. So this quantity is, the denominator is the minimum or infimum of the eigenvalues of my tangent kernel over that ball that I'm considering. But in the numerator, I have supremum of my curvatures, the maximum eigenvalue of my Hessian within that ball. So this is called condition number. It turns out that this quantity is very important in characterizing the rate of convergence of gradient descent to a global optimizer of even essentially non-convex functions. All right, so this guy, what is this? So this is the minimum eigenvalue of the tangent kernel, right? So we know we have a good feeling about it. We know this guy should be large for us to be happy. But what about this guy? So this is the maximum eigenvalue of the Hessian. Hessian is the change in the gradient, right? So we want to have a control on how fast gradients change within the ball. So you don't want to have a very sudden change in your gradient, because in that case you won't be able to have a good characterization of the gradients along the trajectories of gradient descent. So we want this guy to be small. So lower Hessian curvatures are good for us. So in other words, ideally, if we have a genie, then our wish would be, in an ideal situation, this condition number to be small, right? So if this condition number is small, then we can show the convergence of gradient descent to a global optimizer with a pretty fast learning rate, with a pretty fast convergence rate. All right, so let's get a little bit of a feeling about this condition number. Let's first look at the simplest case, which is the linear model. Let's say I have f of w is equal to a linear function times w. This a basically includes x's and every constant that you have. So I have a linear system of equation, or you can think about this as a linear model. And let's say my loss, for simplicity, is just a quadratic loss, aw minus y squared. All right, so what is the tangent kernel? For this, let's first look at the dimensions. This y guy is in m dimension. What about a? No, y is in n dimension. My parameters, they live in an m-dimensional space. Therefore, my A would be a matrix of n by m. All right, so what is my tangent kernel in this case? So I need to look at the gradient of this guy with respect to W. So I'll get A times gradient transpose. So that's basically very simple. So my tangent kernel will be AA transpose. Let's verify the dimension. So the dimension would be n by n, right? So that's the dimension that we want to have. So what about the Hessian of this loss function, the Hessian of the loss? So it is quite simple that you can show the Hessian is A transpose A. So you take the derivative of this, you get a linear function. You take another derivative, you get A transpose A. And the Hessian is kind of similar to my tangent kernel, but it's in a transpose fashion. So it's going to be m by m matrix. So this is my tangent kernel. This is my Hessian. All right. So both of them are PSTs, but interestingly, because one is A transpose, the other one is A transpose A, they will have the same non-zero eigenvalues. Right? Both of these matrices, they'll have same non-zero eigenvalues. Now let's look at the condition number for this system. So again, my condition number is the maximum of eigenvalue of my Hessian. So both of them are independent of W. So we can, get rid of like supremum over W, infimum over W. So in the numerator, I have the lambda max of Hessian, but I know the lambda max of Hessian is the same as lambda max of my tangent kernel, because here, both of them, they have the same non-zero eigenvalues. So therefore, here I can just write lambda max of K instead of lambda max of Hessian. And in the denominator, I write lambda min of K. And this is basically the standard condition number for a matrix. The standard condition number for a matrix is the ratio of the max eigenvalue to the min eigenvalue. So this is the standard condition number of matrix K. Right? So can this guy be smaller than 1?
No.
No, because the max eigenvalue is always greater or equal to the mean eigenvalue. So this is always greater or equal to 1. So if it is 1, it means that all of my eigenvalues, they are the same. So I have like the perfect condition number. If one eigenvalue is huge and my smallest eigenvalue is very small, then this guy is going to explode. So I'll have a poor condition number. So it's very important in a lot of analysis, even in numerical analysis, that our matrices to have good condition number. And in fact, that's what we need in over-parameterized systems as well. So interestingly, over-parameterization helps the condition number, right? So what's the intuition behind that? Why, if I have an over-parameterized system, I'll have a good condition number? Let's assume, so here again, K is A transpose. So it's a matrix like this times it is transpose. Let's assume, just to get an intuition, that all of the elements in this matrix are normal from 0, 1. These are random numbers. So there are some results to show that the condition number of this matrix, it's a random matrix, so I'm going to look at the expectation over different randomizations. The log of the condition number of this matrix is going to approach log of m over m minus n plus 1. So in particular, if m goes to infinity, if I have a lot of parameters, my number of parameters, they go to infinity, my condition number is going to 1. So this is the best condition number I could hope for. And in fact, over parameterization, at least in this simple example, helps me to get a good condition number. Okay, so let me pause and take questions. We have 8 minutes left. Okay. I'm really happy that you guys answering each other's questions. That's really good. Right, so I guess because the gradient of loss function is the tangent to the surface, yes. Since the ball is not convex, Hessian is not PSD, can condition number be negative? So you'll this is the maximum eigenvalue, right? So unless all of your eigenvalues are negative, then you'll have a positive condition number. So if you are like purely concave, then you can have a negative negative condition number in that case. But we'll see that doesn't happen in neural networks. You have both positive and negative eigenvalues. Y expectation will converge to this guy. So it's from a reference. So I didn't put the reference. So in the scribe, we'll add a citation. This is coming from random matrix theory. Takes absolute values of lambdas. Okay. All right. So good. Let's look at. Right. So how much time do we have? Okay, so in the remaining 5 minutes, I'm gonna try to do the convergence proof, and then we'll continue the discussion how we can analyze these condition numbers for neural networks in the next lecture. So let's look at the convergence proof. So the reason I want to do this proof is that I just want to make sure that you guys feel that these are not hard proofs. So these are actually quite simple proofs. Convergence proof. So here we want to show that if you have local PL condition, then first of all, a solution exists, existence of a solution, plus we have a fast convergence rate. Right? So what are the assumptions? So we'll need to make some assumptions in order to do these proofs. We have the following assumptions. I'm going to assume my loss is beta smooth. What do I mean by that? I mean the Hessian, the eigenvalues are bounded by beta. Hessian eigenvalues bounded by beta. They can be negative too, but I want to have a bound on the absolute values of the eigenvalues on the curvatures that I have. And also I want to assume I can satisfy mu PL condition. Right, so basically I have a little bit of a curvature control here and I have a PL control here. So next time we'll see how we can show some of these results, some of these assumptions actually hold for neural networks in general. But let's say we have these two assumptions, nothing about convexity. So these assumptions, let's assume, are true in a ball around my initialization W0 with a radius R, and this radius R depends on my curvature bound, my loss at initialization point, and my mu. Okay, so if these assumptions are true, we'll have basically two results. One is there exists a solution. By solution, I mean global optimizer, right? So I basically say W star, we have a W star in this ball such that if W star is equal to Y, right? So I have a perfect interpolation. So there is a solution. And B, gradient descent, if I run gradient descent with a learning rate, eta, which is inversely proportional to the maximum curvature of the loss in that ball. Basically, you can think about this as 1 over beta, right? So because the maximum eigenvalue is, beta, then gradient descent will converge to W star. What is the rate of the convergence? We have exponentially fast rate of convergence. What do I mean by that? If I look at the loss at the tth iteration, it's going to be less or equal to 1 minus mu times eta to the power t loss at 0. So this is the result that we want to prove. It is the exponential, or some people, they call it linear, convergence rate. So let's understand this guy a little bit better. So what is eta? This is the step size or the learning rate, 1 over supremum of the Hessian eigenvalues. What is mu? Mu is the infimum of the lambda min of my tangent kernel. Right, so this guy is, in fact, if I look at the inverse of this guy, this is my condition number. And that's why we say condition number is important in the convergence of gradient descent or stochastic gradient descent. So if my condition number, if this guy, it's inverse of it, if my condition number is close to 1, let's say say 2, let's say my condition number is 2, the inverse of it, which is this guy, is going to 1/2. So I'm decreasing my loss with an exponential rate of like 1 over half to the power t. So my loss is going to quickly decrease. So in other words, also like the ball that I have, the ball that I need to satisfy these conditions can be very small, because I'm not going to go too far in my gradient descent trajectory. On the other hand, if my condition number is very, very large, let's say it is like 1 million, so the inverse of that is going to be very, very small. So this number is going to be very close to 1. Right? So in other words, when you are doing gradient descent update, your losses, roughly speaking, is going to be the same. It's going to decrease very, very slowly. So having a condition number that is close to 1 is going to be very important. Unfortunately, we don't have time to go into the proof of this. So I'll, basically next lecture, so I'm gonna continue with the proof of this. And then, we are going to show, so far we haven't even talked about neural networks, right? So I'm talking about this general, system of nonlinear equations F. Then we are going to show how in neural networks and in deep learning, some of these conditions, in fact, can be satisfied. And therefore, we can use these results to just like say, we'll have global convergence of gradient descent or stochastic gradient descent. So let me take some questions. Linear because log is taken usually. Yes, that's true. Any questions? So maybe I missed some questions in the chat box. If I have missed it, maybe it's a good time for you to raise your hand and or repost your question if I've missed it. All right, Saeed, go ahead.
My question is, why are we interested in these over-parameterized networks? Because my feeling is that we usually have millions of samples and we don't have that many parameters.
We do. So that's the point, right? So in many deep learning applications, in fact, the number of parameters in the model, it is larger than the number of training samples. And that's a little bit, not basically, the same intuition that maybe we had like, 10 years ago. And we thought that that may actually lead to overfitting. But we'll see that over-parameterization, one, helps in terms of the convergence, because we achieve, roughly speaking, a zero training error. And second, it does not hurt, or it may actually help the generalization behavior of neural networks. And that's something that we'll look into in the generalization lectures. Phil?
So one comment and two questions. This is a really awesome paper. Thank you for choosing it. First question is, can you do a geometric interpretation of the PL condition, perhaps for low dimensional data? And the second question is, I'm one of the scribes for this lecture. Can you provide an explicit reference for the random matrix theory?
All right, so since we are already out of time. So next lecture, I'll provide a little bit more geometric interpretation for the PL. And for the reference for that result, yes, I'll just ping me. So I'll basically send you that reference to include in the scribe notes.
Thank you.
Right, so there's one question posted. Does it help if some parameters are interdependent on other parameters? Yeah, it may help. So as you mentioned, like we want to have a good conditioning number. So I just want to like highlight that the results we are presenting here, I think it is a very important direction, but by no means these are the results that can explain every convergence in any nonlinear systems, right? So we'll see some limitations of these results in the next lecture, but you may be able to think about these conditioning number as a fundamental property of nonlinear systems, that if we have a good conditioning number, therefore we'll have a good conversion. So you may be able to come up with other, maybe architectures or other, schemes or other models that lead to even better conditioning number. So there's a question, can you repeat why condition number is close to 1 is very important in the next lecture? Yes, I'll repeat that argument. But if your condition number is very large, your convergence rate depends on the inverse of this condition number. Right? Let's say if it is 10,000, then that coefficient that geometrically reduces your loss is going to be like, say, 0.99 to the power t. So it is going to slowly reduce your loss. On the other hand, if your condition number is close to 1, then that coefficient is going to be converging to 0 faster. But next time I'll repeat that argument. Okay, I think I took all of the questions. Then we'll end the lecture here, and I'll see you guys on Tuesday to continue talking about this paper. And we'll also, in the next lecture, talk about implicit biases that gradient descent can impose in finding a solution. As you can see in these over-parameterized systems, we have a lot of solutions. But does gradient descent have some implicit bias towards one of or some of these solutions than the others, and how in fact that is important in understanding the generalization? So I'll basically start talking about that aspect of gradient descent and stochastic gradient descent as well. All right, that's it. Thank you, everyone. See you on Tuesday.
Thank you.